the second installment of Leslie matrix models. We're going to build on the first video, and in this one we're going to look at patterns and just beginning to think about how we can apply Leslie matrix models. And what we're doing is using some data from the first video, which you see there right before you. So what we saw in the previous video was to get in year or time period n, the population vector x is that we get the Leslie matrix, and what we do is we look at a previous year, and let's call that x sub n minus 1. So it's the Leslie matrix multiplied by the current or the previous year to get the next one. Alright, or you could write it like this. It's the same idea. So the current one to get the next one. Okay, so that's the same pattern. Now what I don't think we covered in the previous video was, what if we need to zoom up to here without going through all the subsequent years before that, before all the previous years? If you want to go straight to the 10th after 10 years, what do we do? Because we might only have this data here, the initial data. What if we want to find x sub 10? Well, you could use those processes that I've just written down, but a much quicker way is, because it's repeated multiplication, if you think about it, what we do is we start with this one, we got L multiplied by that population vector there, and you get x sub 1, and then we repeat that. What we're doing each time is putting the same Leslie matrix on the front, so essentially it's repeated multiplication of the Leslie matrix. And from our previous work we know we can raise matrices to power. So in general, if you want a particular population vector and you want to go straight there, instead of going through all of the individual time periods, you can simply do this. So Leslie matrix raised to the power n times the initial population vector, if that's what we've been given. So that if we were given this one, we could go straight to this one. Okay, so we use technology, of course, there. But what if we're not given x sub 0? What if we're given that instead? Well, this pattern, we can expand on this pattern. So to get x sub n, provided you've got the Leslie matrix, you raise it to a power such that, we'll call that j, and multiply it by whatever population vector you've been given, let's call it x sub k, provided that j plus k, those integers or natural numbers, j plus k equal n, the pattern will work. So the subscript on the X matrix and the power on the L matrix, you add them together and you will always get the year population vector you're chasing. So the little j plus k equals n. They're just arbitrary symbols, but the pattern is real and it's very useful too. I would recommend that you pause the video and here with your graphics calculator and verify those patterns and see if you can get the various population vectors you see in front of you. Okay, so you could try all of these patterns here. There's 4 of them. They're all handy in their own way. Why don't you try an example of each and see if you can get those population matrices. Other things we can discover about Leslie matrices is that in the long term, and there's no magic formula about what long term means, but after many cycles, big values of n, for example, in a certain situation it might be something above 20, or in other situations it might need to be a bit bigger. When n is large, now again large It's a little bit grey that, but when n is large, you'll see that the population actually, the annual population or annual increase, or whatever the time period is, it could be quarterly if it's insects. But let's say it's an annual cycle, like with the possums. N is large, you'll have a basically a stable or a settled annual increase. Now if we go back to our data here, if you look at it all, it settles to about, after a long period of time, if you got X sub 10 and then you went a bit beyond that, eventually it settles to a figure of 29% approximately in this one. That's here. Now that's not, 29 won't be in every model, that's just in this model that we're looking at with the possums. Okay, 29 is only particularly for this model. Other models will have different percentages, but the thing is, it stabilizes. Okay, the annual or other time period, whatever the natural time cycle, it might be decades. Oops, time cycle. Months, if it's little insects or something, or decades if it's people. In this case it's just years. That's why I'm saying annual increase or decrease. It stabilizes. In other words, it converges to a value and it sticks to that. So that's a general property of Leslie matrices. And it's a general property of Leslie matrix model. Okay, so in the long term, the annual increase or decrease, bearing in mind it doesn't have to be annual, it can be decade or whatever the cycle is, it does stabilize and it converges onto a value. So you get convergence. Hope you can read that word's convergence. Okay, so it produces a stable state, another way of describing that. So stable state or a stable rate of increase or decrease. So eventually we get x sub n after large values of n is some k, some constant, times the previous one. So from one cycle to the next, we're getting the same scalar multiple of for the population. So here, in this case here, we'd have to use k would be 1.29. And in fact, if I go to some more decimal places using the actual data, because there were actually more decimal places, the graphics calculator here was just set to tenths, but if you use more, it's more like 1.2922. Okay, so that was in this particular case here. So the pattern, however, even though k will vary depending on the model, that pattern will happen eventually. So the annual increase or decrease will stabilize, and also the age populations. So age populations also. And that's the proportions of each. Okay, the proportions. So the proportions of each age category will also, oops, I got also there twice, also will also, let's get rid of that one, will also basically stabilize. They'll converge to a certain number. We'll have a look at that in a moment. So if you actually use the numbers from this video and the previous one, you'd find that eventually the proportions would converge and stabilize. So the 0 to 1 would be pretty much 50%, and you see all the other values there. Okay, so that is again a feature of Leslie matrix models. As an application, sometimes in real life scenario we'd need to look at a culling factor or harvesting factor if it's a case of population getting too high. If it's getting too low, they could introduce, remove or introduce the various critters or plants, which would have the opposite effect. But if the populations get too high, we might have a culling or harvesting factor. But what factor? We need to do it in a controlled way, so we can't just obliterate kangaroos without any planning. So, and some people would say we can't obliterate kangaroos at all, but that's a completely different argument. So if harvesting does happen, and if we use the 1.299 that we've been using with the possums, it doesn't have to be killing anyway. It can just, whoops, I got the wrong number there, 1.2922, sorry, 1.2922. It can be removal too, that can happen. What we need is basically this, using that value, and remember that value it varies depending on the model, but if we use that, we've got 1.2922 times 1 minus h. Now h is the proportion that we remove. Proportion removed through shooting or physical removal, or whatever procedure is being followed, and that h actually becomes the culling factor. So we use k in order to find h, and k was that stable state growth. We basically need to put in a compensatory factor, so we get 1 will mean that the overall population is not growing. Right, so even though the growth rate stabilizes, that stable growth rate might be too much for an environment, and when things are overpopulated, they run out of resources and the entire population suffers. So it's sacrificing a few for the greater good is the reasoning behind that. And again, you're free to disagree with the ethics of it, but this is the maths of it. Rearranging, we get that, and evaluating, we get 0.2261. So that's the proportion we need to remove. So the culling factor, if we write that as a percentage and just round it to 1 decimal place, we have 22.61. Let's go to 2 decimal places. 22.61% culling factor would have to be applied in that same period, which might be annually. Consolidating some of these ideas by just looking at some other data, just to finish the video off. For this Leslie matrix here, in this model given, it's a different one to the one we've been looking at. It's smaller, simpler, but different in its features. So you can see that we have the birth rates across the top there, and survival rates down the side, and initial population vector quite different. It's got 1,000 of the youngest and then nothing of the older, so that's quite a different one. And now what we're doing is going for big values of n to look at the long term, and we're seeing what happens to the population long term. So you can see that we can go straight to the population at 25, whatever the cycles are, 25 years or whatever we're talking about here, and we can then do the same for 26 and have a look at the differences here. Now we're comparing the youngest age group in each case as a ratio, with comparing the middle and comparing the bottom age group. You can see those fractions there, and that's the annual increase each year. So it's about a 19% increase each year, and they're all exactly the same. If you enter that into the calculator, it's no lie, that's exactly the same. So that's an interesting, so after that does qualify as long term, 26 cycles. Okay, so that's sufficient. If you went higher values, you would it would stay pretty much at that 19% growth from year to year or cycle to cycle, depending on the duration of the cycle. So we see here that all of the age categories are growing at the same rate, and that will stabilize the total growth rate of the whole population if they're all the same and they're growing at the same rate. And that will also follow that pattern that I pointed out a bit earlier, that the population proportions will stay the same. I can show you that in just a second. So our findings here, long-term growth really is dependent on the Leslie matrix, okay, and you can verify this by trying different initial populations, different X0 matrices to verify that if you like. You'll see that you'll still get that growth rate the same. It's dependent mainly on L. It has the biggest effect. Also, we see, just to finish, that if we get these populations here as a proportion of the total, this basically reinforces what I said earlier, and then we put the total on the denominator, we see that this is 0.770492, which is 77%. And then if we try it with this other matrix here, we get this here, which you can see the same calculation, and look at that, exactly the same value. Amazing. So there we go. There's some features, information about some ideas to do with culling, which is an application, long-term growth, stabilization, and various efficient ways using various modes of calculation, all the while using technology.